G'day everybody and welcome back to my channel. I just want to go over a couple of things because I lost one segment of this video that I'm uploading now. It's, how do I explain it? It's a whole load of small bits of work that I've done over 2 days when I've had time, and I lost the very first opening segment where I was saying hello and explaining a few things. So I've made a little bit of a list just to go over a couple of things. Anyway, I'll actually just move this just to look over here for a sec. First thing I want to mention is the load resistor is now connected instead of at the output of the series pass element. It's connected at the end of this 1 ohm leakage sense resistor. The next thing I should point out is also why there is a 1 ohm current leakage sense resistor there. Okay, so this wire here goes off to the tap changer board. This red wire here goes off to the reference board, which goes to the base of that transistor. This yellow wire goes to a panel meter. This green wire goes to a load resistor. Point being, all of these four things have some sort of current draw, whether it's continuous or a capacitor building its charge up, it still pulls current from the output. Now, because I want the constant current circuitry to be really accurate, I want to sense the leakage current that's flowing out the output terminal and into other bits of the circuitry. I want to be able to measure that, sense it, and deduct it from the measured current from the output via the 0.050 ohm current shunt. Sorry if I've been a bit stuffy the last few days. I've got a bit of a cold. It was one of those weird colds where you don't get a sore throat too much, which I actually like those colds more than the ones where you get a sore throat. But I did end up with a blocked nose for like a week. I still have a blocked nose. It's a little annoying. My apologies. So that's why the 1 ohm resistor's there. Now, something else I spotted. When I removed the OR gate diodes and the capacitor across them, all my accuracy came back. 1 millivolt, or less than 1 millivolt accuracy down the bottom end, going up to around about millivolts at 10 volts, and about 8-9 millivolts it ended up being at 30. Something dawned on me. That was still higher than how I had it at first when I first made it. And I was sitting there thinking about this last night, and it is. I actually had it down to like a couple of millivolts, like 2 or 3 millivolts at the top end, and nothing at the bottom end, like microvolts of deflection under a 5 amp load. Well, I spotted the problem. I don't know if you can see there's 3 contacts there that suspiciously look like if you took one of these 10-turn pots and bent pins over, with them spaced out evenly of course, it would fit there. And that's exactly what that was for. I had, I can't remember, a diode, a resistor, a pot, there was a few components there. And I can't even remember because it was so long ago. I'm going to have to go look through my own notes and whatnot. But I can't remember for the life of me how I implemented the circuitry, but it was basically offset adjust and allowed me to make it so the comparator could have sort of a non-linear gain to it, so that I could adjust offset at the top end without affecting it too much at the bottom end. So I've got to look through my notes. I've got a whole folder here. all the way through designing this thing from that. Like, that's not even how the tap changer is now. There's way more stuff in it. Like, it doesn't even use transistors. There's heaps of components submitted. But as I was designing it and, you know, having problems, I would, you know, take notes of stuff, you know. So I've got this huge folder of just pages of almost illegible writing, because my writing is really messy. But I can go over that, and, you know, it will give me some sort of idea anyway. So okay, I've already found the page. There we go. It looks like I had a couple of diodes going from the base of the transistor going to a 50k pot, which went to signal ground. Apparently I was trimming offset like that somehow. I remember I was trying to use the diodes to thermally compensate the transistor, but I've ended up doing that differently. I've decided to ovenize it instead. Yeah, okay, so I know exactly what I need to do there. That's a really simple circuit. All I remembered was that there was a pot and some diodes, or a resistor or something. Yeah. So I think I'll be able to improve the accuracy just a little bit more, which is a really good thing. What else did I have to go over? Okay, so what I'm up to doing now is thinking about how to implement the constant current circuitry. Sorry, not implement it. I've actually designed one all out of transistors and one out of op amps, so that in my upcoming power supply builds, I've got a good circuit design to use. Anyway, including in this one, I've got to work out a way of getting it to fit in here. As you'll see watching this video, like I said, I missed my starting segment. I deleted it by accident, and so I may be going over a few things here that I've already gone over in the video later on. My apologies. I get the feeling I am right now, but yeah. Anyway, I guess you'll see what I don't really need to explain about that, because that's what this video is about. The other thing I have to decide on is, as you'll see in this video, how I'm going to implement this driver board's, it's not really an OR gate, but you could think of it as an OR gate, the second way of adding constant current into the circuit. As you'll see in this video, there's a problem with that, because it turns out there's two sources of current to the output terminals. I know that sounds funny. You think it all comes through the series pass element. About 27, 28 milliamps actually comes from the reference board. And that's the sort of problem caveat that I've got with this circuit, as you'll see in this video. So without further ado, on with the rest of the video. Enjoy. Alright, so I've come up with a solution for the diodes. I'll just move this out the way. That's a 3.3 volt Zener with a 1N4148 in anti-reverse, whatever you want to call it, to it. You know, so current can't flow from the base to the emitter through the Zener's inherent normal diode direction, but once the voltage from the base, from the emitter to the base exceeds 3.3 volts plus one diode drop, it will shunt the current over the junction. So that protects the base junction. The reason I end up going with the Zener is it's not going to cause extra noise, and it doesn't. And the reason for that is because it's only going to come into operation if a very sharp pulse comes back in a negative terminal and wants to go up the emitter. And if there's a sharp pulse already that big that's going in the terminal, it's going to be bigger than the Zener noise for the moment that the Zener turns on and fires. So that's not going to be a problem. Also, it's another two components that don't need to be thermally ovenized anymore, because having just a row of diodes means that they're always slightly in conduction, unless made like a huge stack of them. I'm not too sure about that actually. No, because you don't. Yeah, no, you don't get complete blocking in one direction until a threshold voltage. So I would have had to ovenize the diodes, but with it like this, I don't have to ovenize it either. So now the only two components, or actually might only be one component, because depending on how I implement the feedback loop for the constant current circuitry, if this transistor ends up being in the feedback loop, which it most likely will be, it won't need to be thermally ovenized, compensated. So that will literally just leave that one transistor there, which means I'll probably be going back with a resistor just heat shrunk with thermal compounds in it, 100 ohm resistor, heat shrunk to that TO92, and I'll also heat shrink, I don't even know, I don't even think I'm going to put thermal regulation on it, to be honest, because in my mind, if I run it off a fixed voltage current supply that doesn't change, the resistor always runs at a certain temperature, and I just set it so that it's enough above the ambient fluctuation. Although no, that won't work out well, because ambient fluctuations will add to the temperature, won't it? Yeah, no. So I'll put in that sleeve, I'll put feedback and a resistor as a heater. But it looks like it's just going to be. So I'm balancing my phone and stupid angle. It looks like it's going to just be one transistor that I've got to ovenize. So that's pretty cool. Anyway, I'm going to continue on with designing this, and I'll report back soon. Okay, so I just changed the 3V6 for a 3V9 Xena, still with the 4148 diode. Now that keeps it well out of the conduction area, with the maximum base to emitter voltage minus the 4148 diode drop, and I don't need to thermally compensate them at all now. I can heat those diodes up and the output voltage doesn't change. So that's that bit dealt with. I've got a 2 transistor, say, OR gate basically. It's not really an OR gate, but it's functioning as one. One's a comparator and one's a second input to a pull down. It's kind of like having an OR gate. You know what I mean. Anyway, I'm going to now work out how I can get that transistor to switch on enough to pull the current all the way down. If I can't, I'm going to use a FET or a different transistor, or we'll just have to see. Alright, I'll report back soon. Okay, it's finally dawned upon me what's going on here. Now I got the voltage turned up all the way, and it's 11.191 volts. With the circuit, with the trace cut open before the 1K resistor that goes to the Darlington output, with a transistor in series with it that's currently lifted so it's open, so nothing going into the output stage to bias it on, that voltage is present at the terminals. And I just dawned on me where it's coming from. Because the reference board down here, because the reference board's positive terminal goes through this 1 ohm resistor and to the positive terminal, and its negative, its negative goes to the base of this transistor, flows through the base to emitter junction, and guess what the emitter connects to? The negative terminal. So what I'm thinking of doing, you see that 1K resistor that's right there? I'm thinking of putting a constant current source there, a thermally compensated one, like an LM series 3 whatever, I can't think, to limit the current there to 1 milliamp. And then here's the caveat to that. Will 1 milliamp be enough to drive the base of that, because this needs to go up to 30 volts, 5 amps. So enough current, which is limited by this resistor from this power supply, is fed into this driver transistor, so that when it's turned off, that resistor turns the output on and allows that amount of current, or just a little bit over, but it's so that it's crudely limited before the current limiting circuitry is even added. So I'm going to go and do that now. That 1K resistor is going to come out. Constant current source is going to go in there. See if 1 milliamp will do the job. The other concern I've got is there are two 10 microfarad electrolytic capacitors right there, and two 1 microfarad monolithics, for a total of 22 microfarads. That voltage there needs enough, that capacitance there needs enough current and voltage, i.e. power, to charge it up quickly enough. It doesn't affect the response time of the power supply, but what it will affect is when you turn the voltage up and down, how quickly it goes up and down, if that makes sense. And with a 1K resistor there, it's decent, you know. It's not the fastest thing in the world, but like I said, that doesn't affect. Oh, actually, there's no regulation on it, so this is not really worth doing right now with the regulation circuit open. But it doesn't affect regulation. So I think there's about. Well, let me just put the camera up here, and we'll see how much current there is there right now. I might just turn this down, because the reference can supply 29.4 volts. And I don't want to pop not the TL431, that's not what's driving it. There's a transistor back in there that's buffering the output of that. And then there's feedback off the output going back to the TL431, so that it's a closed loop circuit that powers the pot. So if the load from the pot and the feedback circuitry increases, the TL431 voltage won't change. Or the series pass transistor on that board's output won't change. Anyway, what was I going to do? Oh yeah, measure the current between these 2 points. Let's start turning this up. I don't want to go more than that. Let me just fill this series pass transistor. How's the 1K resistor? Might be able to get away with this. Oh, I don't really need to. I can already tell from looking at that and what we saw before, it's about 28 milliamps. So here's the thing I've got to work out. Do I need 28 milliamps to feed the base of the comparator transistor? So all I can do is, I guess a crude thing I could do, a crude test is, before I go and muck around with a current source, is just increase the value of this resistor until when the reference voltage is turned up to maximum, there's 1 milliamp or less there, and see if that's enough to drive that comparator transistor hard enough to turn it on enough to turn the output down to the low end of the voltage scale that it's designed to go to. So I guess I'll do that now. I've got a 1K in there. I'll take that out, I'll put a 10K in there, we'll see what that does. Do you want to watch? I don't know. I don't know if I should pause the video and do it off camera. Should I do it on camera? Pause the video. Alright, so I've just put a 10 ohm resistor in series with that 1K just to bypass that open there. The 10 ohms is not going to make a difference. I could put a higher value than 1K and it would still not make a difference. That's fine. It's a 4 Darlington stack up. The gain on that is insane. Like, yeah. Anyway, I've got the 10K down there. I've got my load bank hooked up. There's also some capacitance on here, plus the output capacitance of the supply. I want to say two things. How slowly it comes up to voltage with 10K in series with those capacitors, if that affects that. Although it's not really a problem unless, actually yeah, it's not really a problem unless it affects the feedback response. Let's see. Yeah, it slows the pot down. I don't think it's going to affect the feedback speed, but maybe a little bit. That's alright, I can adjust capacitor values. Alright, well, and the voltage being a little bit shy. Look, I can turn the reference voltage up a little bit, but I'm more worried that that's a lack of current and it's not going to be able to supply 5 amps. Let's turn the load on. Yeah. That's just those capacitors discharging down there. Yep, so that's a bit of a problem. I can't just put a current source in there. Alright, I'll have to try something else. I'll be back soon. This is the fun of engineering stuff. But that's what my channel is basically all about. It's an engineering and repairing blog. I'm either designing stuff or I'm fixing stuff, so that's what it is. Okay, so I put the 1K resistor back in there. I've taken that 10 ohm out where I've made a break in the board. Incidentally, see, this is why I like prototyping like this. I'm not saying I don't use breadboard, and let me just say one thing about breadboards. This constant current circuitry, which might not end up going in this anyway, we'll get to that in a minute. These old breadboards that are brass, I've never had trouble with them. I find as long as you keep the contacts clean with like cleaner and don't touch the copper wire with your fingers so it doesn't oxidize. I've made up precision circuitry, you know, it's like 0.1 ohm current shunts going into instrumentation amplifiers, 0.050 current shunts going into OPO7s, stuff like that, you know, with offset nulling, all sorts of stuff. And I've had no problem on the brass breadboard with these new ones that have got steel strips that are chrome plated. Excuse me. They're terrible. You just go like that and everything turns to shit. Well, when I prototype like this, etch a board up, you know, I just add, if it's like a board I know I'm going to work on a lot, I add a whole load of extra bits everywhere so that I can cut tracks and add stuff and play around with it. At least when I find, say, a voltage offset somewhere or something like that, or a current offset, I know it's down to one of two things. The actual resistance of, say, a switch contact or a piece of wire, or it's actually there because of the way the circuit's designed and I need to do something about it. If I'm working on breadboard and there's some offset current or offset voltage flowing somewhere, it could be coming from any one of those holes on the breadboard because of all the loose contacts. So that's just, you know, each to their own. You do what you want to do, but this is why I like to do it like this. And I find it's neater and more secure than just tacking components together, you know, like say you want a base to emitter resistor, you know, and you just tack it like that, and you got like another resistor on the base like that, and it's all just a huge, I forget the term of it, you know, but yeah, that's why I do this, Anyway, so what I'm going to do now is I'm going to put just a little link, 0 ohm link, in where the 10 ohm resistor was. I could probably just, I could just leave the 10 ohm resistor there, but anyways, I'm going to put a link back in, and what I've come up with the idea of is basically, if I'm going to, what do you call it? If I'm going to try and do this, what I'm trying to do, form a spot to insert the constant current circuitry's control end, if that makes sense. I've decided, well, if the reference, I might need to use 2 transistors to accomplish this, sort of, not in series with each other, but it's kind of hard to explain. What I'm thinking is, obviously if I open up that there, or shunt that there, that pulls the comparator current all the way down, and hence the drive transistors are turned off as much as they can be. If I simultaneously implement something that opens up the reference circuit, well, not opens it up, but makes it so that, say there's a device in series with the output of the reference circuit, like for example a transistor, and you know, I can do anything from completely open up. Why is this wire not tinning? And yeah, I know this is the wrong soldering tip bit for this, but anyway, that'll do. I just forgot what I was saying. Oh yeah, if I have in series with basically this red wire that comes from the voltage reference, if I have a, say a transistor in series with it, some sort of device that I can, like I said, open it up completely or control how much current's flowing into it, I can use that. Like I can have that device controlled by the constant current monitoring circuitry in combination with a device across here, for example. I'd rather do it with a device across collector to emitter on the comparator transistor than in series with the output of it, because in series of the output of it is going to play with the regulation. Actually, no, it's not, because that's in the feedback loop. Yeah, so I could do that either way. I could put a transistor there, or I could put a transistor there, but I also need one kind of in series with this. And there lies the next problem. If I put a transistor in series with that, is my noise figure going to go up? Because I remember when I put a diode OR gate in there, the noise figure went up, and then I had to try and capacitively couple it, and then that killed the reaction timing. So I've got a few things to think about here, but at least I've worked out what I'm going to have to do. Basically, I need to find a way of limiting the output of the reference board even when it's turned up to full, so no matter what it's set to, I need a way of limiting its current output. to the base of this transistor, and I need to simultaneously have a transistor across here like I did before that's also getting controlled at the same time as this other transistor I'm talking about gets controlled. I hope that makes sense. I'm going to have a think about this and see if I can come up with some other method. I guess the other thing I might be able to do, because the reference is in reverse, I might be able to create an extra bias network to this that biases it on. Hey, this is actually a good idea. Yeah, I might be able to make another bias network that biases that transistor on, so that the reference board has to overcome that bias, right, to turn it off. I don't know if this is doable. I'm going to have to experiment with it, but if I can do that, then all I'll need to do is put a transistor in series with the reference board, and that will be able to go to the constant current control circuitry. I'm going to go do some thinking off camera and a little bit of experimenting. Okay, so I've done a little bit of playing around, and I've come to the conclusion that I'm going to have to change the design of the comparator just slightly to the design that uses two transistors, and I'll just move over here a little bit. So I can fit here and explain what I mean. Actually, that's not very good, is it? One moment. That's better. So instead of the reference feeding power into the output, right now where I have that 47k resistor coming from the regulated supply, that goes down to the collector of the comparator transistor, and that goes to the output, negative output terminal. Now, instead of having the reference basically adjustable with a pot, but instead of having the reference in between the base and, let's just put the positive output over here, instead of having the reference in between these 2 points here, like this, if I grabbed this piece of paper and it went. If we take our same 47k resistor from the regulated rail, these both still go to the negative output, but now basically one of the bases looks at the positive output, the other base goes to our adjustable reference, if that makes sense. That way, although the reference will still be referenced to sorry, I'm I haven't designed this yet, obviously, so I've got to think. I'm just trying to think. I think the reference will be referenced to the negative rail. I can't think. Or I might use a floating supply to implement this. But this is what I'm going to do. So the reference current will basically flow from some other point to ground, but it's not going to be able to flow between the positive output through that transistor and the negative output, which is the problem we've got now. There's additional current flowing between the output. So even when we turn this hard on to turn off the series pass element, which is driven off of there, we still have this current here from the reference, right? But if I make a 2 transistor comparator, I can sync the reference current from, it doesn't matter if it goes to one of the output terminals and back to the capacitor bank, it just can't be in between both the terminals, if that makes sense. So I can do that way. So I'm gonna redesign that circuit a little bit. So that's my solution. So in the next video you'll see that. This is the fun thing about designing. Incidentally, I've got a lot of parts rocking up for my own amp builds, which I'm not going to probably start straight away. Or I might. I think I will actually. Once I need to get stuff off the bench, and I want to fix my multimeter. So when the parts come from my Tektronix DMM916, I'll do that. And when the parts rock up for that Yamaha mixer, I'll do that to get it out of here. And that'll happen in the next couple of days. But apart from that, I'm going to keep working on this. Alright, well, thanks for watching. And I'll see you in the next video.